Okay. First thing we talked about in the physics units. Okay, first thing that we talked about were the types and forms of energy. All right, that was in that handout, or it was in your notes. It wasn't a handout. It was in your notes, and it looked like it was photocopied out of the textbook. Okay, because it was. It's fair use. I'm allowed to copy a certain percentage. Okay, so what we were looking at that day was what's energy, what's work, what's thermodynamics, what's thermal energy, all that kind of stuff. So it was kind of the laying the foundation for what we did in this unit, knowing what energy was, what kind of things are energy, okay, and things like that. So I would say types and forms of energy and that kind of vocabulary, terminology, that kind of stuff, okay, I would say if you're looking over those notes, study them as you would for a multiple choice type of recognition question. All right, so if the question's, talking about, let's say, what type of energy would be stored in, or would be available in a can of gasoline, okay? Well, that would be what kind of energy? Chemical potential energy, yes. Okay, so that's kind of what it'd be a recognition thing and understanding that this is this type of energy, that's that type of energy. Okay, what kind of energy would be in, let's say, wind? Okay, well, wind would be what kind? Yeah, kinetic. I would also say if mechanical was an option there, you could probably also say that. I probably wouldn't put them both because they'd both be equally right. Okay, so things like that. That's kind of what you'd be looking at there. Am I going to ask about some of the people? Probably. Okay, so you'll need to know, about Seebeck and Oersted and Faraday and guys like that and what they did. Again, just enough to recognize, okay, what they did, right? Stuff like that. Okay, so we talked about how Oersted, he did the current carrying wire, okay, that had the compass under it, right? Okay, that kind of stuff. Faraday, he did the electric fields and magnetic fields and how one could cause changes in the other and things like that, right? So those are things you need to go over there. Okay. We also talked about that day the different types of systems. Okay, and there were 3 systems. Okay, there were open, closed, and isolated. Okay, again, that's going to be multiple choice type stuff. Be able to recognize if I'm which one of them I'm describing. Okay, in the stem of the question. That doesn't look like an E at all. Now it sort of looks like an E. Okay, and that day we also talked about the first 2 laws of thermodynamics. Okay, so thermodynamics is pretty important in this unit. Understanding, how energy flows. Okay, second law of thermodynamics says it flows from hot to cold, right? Okay, and that's thermal energy, flows from hot to cold. If we're talking about mechanical energy, it's from a high energy object to a low energy object. If we're looking at like the first law of thermodynamics, that's the law of conservation of energy. Okay, we got to understand, be able to recognize those, know what they are, but also think of some applications of them. Okay, we did a lot of stuff, questions from that handout, okay, that had to do with, is this situation talking about the first law, or is this situation talking about the second law of thermodynamics? Okay, and we talked about heat engines and heat pumps. Okay. Okay, we talked about how they both are governed by the laws of thermodynamics, mostly the second law of thermodynamics. Okay, a heat engine uses that flow of energy from one place to another, okay, in order to run, but a heat pump goes against it, like an air conditioner or refrigerator. So I would say probably know stuff like that to be able to recognize, or you might even be asked to explain. Okay, there might be a written response item where it's explain how this situation obeys or doesn't obey the laws of thermodynamics, okay, things like that. One of those situations was these. Okay. Yesterday we talked about efficiency and we said no energy conversion can be 100% efficient. Okay, that's part of the reason why a perpetual motion machine can't exist. It's converting energy from one form to another, so it's always going to be losing energy. Okay, and energy flows from a high energy object to a low energy object. If the perpetual motion machine is the high energy, it's going to be losing energy and it's going to stop. Okay, the other problem was a perpetual motion machine can never do any what? It can't do any work because it works a transfer of energy and it would lose its energy and stop. Okay, so things like that, things to think about how those things work. Okay, that was kind of the first couple of days of the unit, so all about the basics of energy and thermodynamics. Okay, then we got into the more mathematical parts of physics. Okay, and we talked about scalar and vector quantities. Now, scalar quantities, what are some examples? Speed is one. Distance. Okay. What else? Time. I was just going to say, by not giving me an answer, you're wasting it right now. All right. Time. So, those are our scalar ones. Okay. Now, one other one that's scalar is energy. Okay. We didn't talk about it right away. Okay. But energy is a scalar quantity. Right. Vector quantities. Okay. Velocity. Displacement. Acceleration. One other one. We didn't talk about it very much. Mostly to do with the work-energy theorem. Nope. Not efficiency. Starts with F. Force. Okay. So why do I go over these? Well, I mean, there might be one multiple choice question that says, like, which of the following are vector quantities or something like that. But more important than that, on a written response item where I say, calculate the displacement, it's kind of important that you remember that displacement is a vector quantity, because if you don't, you might calculate distance by accident, and then you won't get any marks. So knowing which one's which is pretty important, okay, because it does change the way you would solve, okay, a problem. So it's important to know which one's vector, which one's scalar, which ones go together, okay, things like that. So keep that in mind, okay. And my recommendation when you're going through a physics test, guys, is, okay, don't start answering the questions right away. Read it through, especially the written part. Okay, read it through with a highlighter. Bring a highlighter to the test. Okay, highlight the things that are important. I usually boldface them or underline them or something like that, but you should highlight them and then maybe write next to the question vector. Okay, things like that, just to remind you. Oh yeah, this I gotta remember direction matters. There's some positives and negatives in this question that I have to take into account. Things like that. Make little notes beside them. The first time through, you should just read the questions. Okay. And I say that because I'm a physics teacher, guys, and I know that it works. Okay, I see people do it. When people hand in tests, there's scribbles and highlights and stuff all over their tests. Okay, and that's a good thing because they've analyzed the question and thought about it before they just knee-jerk reaction figured out a way to do it. Okay, always better to think it over. So recommendation for you there. All right, that same day, okay, we didn't talk much about acceleration and force and energy that day. We talked mostly about this and this. Okay. Can you expect to have a V equals D over T problem on your unit exam? Yeah. Okay. It might just be a multiple choice question because it's not a very hard calculation. Okay. But certainly your ability to use speed equals distance over time and velocity equals displacement over time, yeah, you're going to be tested on that for sure. Okay. And then we talked about graphing. Is graphing going to be important? Yes. There's lots of graphs on this test. Okay. Some of them in the multiple choice, and some of them in the written. Okay. How many types of graphs did we talk about? We talked about position versus time and velocity versus time. You have a lab on each one. Okay, you have the Need for Speed lab, okay, that was on velocity versus time. You have the graphing lab with the little carts from the atrium that was on position versus time graphs. What you guys need to remember, okay, is what can I get from each kind of graph and how do I get it? All right, because I guarantee I'll ask both. Okay, so you better remember, how do I get displacement from a velocity time graph? Okay, and if you're not going to memorize it, and I don't recommend that you do, okay, just work through some graphing questions and go, right, okay, I've got meters per second. Okay, so in a velocity time graph, right, I got meters per second here and seconds here, and if my line goes like this, and I want to calculate displacement, well, this is speed, this is time. Okay. So I would multiply these two things, because that would give me displacement. And meters per second times seconds, the seconds would cancel, and that would give me meters. What am I calculating? Area under the line. Okay, so things like that to remember. Okay, the slope of a line. This object here, is it traveling at a constant speed or accelerating? That's supposed to be flat. It's traveling at a constant speed. Okay, so if it's traveling at a constant speed, what's the slope of this line? 0, right? It's flat. Has no slope. That's why the acceleration is 0 for this object, because the slope of the line represents acceleration, because it's meters per second, or meters per second squared. Okay, so you're going to have to do some analysis like that. Okay, so you definitely want to review your graphing stuff. All right, there's a lot of marks to be had on graphing. Okay, for the position versus time graphs, you got meters and seconds. Okay, so slope of a line there, what would that be if this is in meters and this is in seconds? Yeah, speed or velocity. Okay, if it's a vector quantity, like it goes down, right? Okay, so we're looking at velocity there being the slope of that line, because it would be meters per second when we do rise over run. Okay, probably just have a look quickly at this as well. Okay, it's a little more robust and will do a little bit more for you than rise over run will. Okay. If on this graph, question asked me to calculate the displacement between these two times, let's say it's 1 second and 5 seconds, how would I do it? Does this graph show me where the object is at all times? Yes, it does. It's a position versus time graph. It tells me the position of the object at various times. So if this is where the object started and this is where the object finished, okay, then I should be able to go displacement equals final position minus initial position. Agreed? Okay. Now, one other thing with the graphing questions. If I give you a graphing question that not only has a graph, okay, and I might give you a graph that has mistakes on it and ask you to tell me what's wrong with this graph. Okay, maybe it's missing things like, we said there's some really important things that have to go on a graph, right? Like labeled axes and scales and stuff like that. Okay, but I might also ask you to do some calculating with it. Okay, and I might ask you what's going on in this section of the graph, what's going on in that section of the graph, so based on shape, okay, things like that. But the most important thing, guys, is if I give you a graph, but I also give you a table of the data the graph was made from, okay, and then in a question I say, let's say for example this is a position versus time graph, and I give you a table that's got the positions and the times, okay, and then in question number, let's say, or part A of that question, I say calculate using your graph, calculate the speed of the object, okay. Should you take the biggest two numbers here and divide them, or should you use the graph? You laugh. You wouldn't believe how often I see that done. If I say use the graph, okay? Because usually what I'm saying is the last point that's here isn't on the best fit line. Okay? So always read the question carefully. Okay? And I'm not saying that to belittle your intelligence, but you wouldn't believe how many people on a test get a little bit stressed and just space on something like that. Okay. All right, after graphing, What are we on now? 4? Okay, we're on to acceleration. Gonna have an acceleration problem to solve? Most definitely. In the written response, you're gonna have a problem to solve that has to do with that. Were there any little tricks with that formula? Like some terms that we might use that might stand for a number? Like, let's say a boat moving at 5 meters per second comes to rest in 5 seconds. Right? Remember, if something starts from rest or comes to rest, rest means it's stopped, which means the velocity is 0 at that point. So just little terms like that. Okay, we got to remember. What about if I drop something? How fast is it going when I drop it? How fast is it going right now? 0. Okay, if I'm dropping something, the initial velocity is 0. Okay, that might be important. Once in a while, I make a hard question. Well, it's not really all that hard, but if people don't read it carefully, they forget. Okay, a little thing like that, and then can't figure out how to do it. If I say something is dropped, I've given you one of the givens. Okay, I just haven't outright said the initial velocity is 0. Okay, everyone with me there? All right, so yes, you're going to have a question to do with that. You may even have to use that as part of a graphing question, okay, because velocity versus time graphs can show acceleration. That's where we get that formula from, right? That's the slope of the line on a velocity versus time graph, right? y2 minus y1, right, over x2 minus x1. That's where we get that from. Okay, and then after acceleration, then we moved on to energy. Actually, we moved on to work. How much of this test do you think is going to be on work energy theorem? Yep, it's actually pretty close to that. It's actually pretty close to 40%. Okay, the last half of this unit was all about work and energy. You have to expect that half of the test is going to be about that. Okay, there's 2 work energy theorem problems. There's a law of conservation of energy problem, and there's several questions. By several, I mean lots in the multiple choice that deal with energy, right? So and work. So yeah, you definitely need to know your work energy theorem stuff. Now, the good news is all of the work energy theorem questions and all of the law of conservation of energy questions work the same. Okay? The big deal is remembering which one is which. Okay? How can you tell a work energy theorem question from a law of conservation of energy question? Right. We're always going to be dealing with 2 different positions where the mechanical energy is the same in a law of conservation of energy problem. Okay. What are some things you're going to be given in a work energy theorem question you wouldn't be given in a conservation one? Force. Force is a big one. Okay. And in a law of conservation of energy question, if the energy is not changing, what's not getting done? Work. Okay. So if you can obviously tell that only one type of energy is changing, it's probably a work energy theorem question. Okay? If both types are changing, it's because they're changing into each other and the mechanical energy isn't changing. That's a law of conservation of energy problem. Okay? If you've got something being lifted to a bigger height, well, that requires energy to be put in. Okay, that's a work energy theorem question. Okay, if something is being accelerated by being pushed, okay, or being shot or something like that, that's a change in energy. That's a work question. All right, so it's situational. That sort of makes sense? Okay. So yeah, and this one here, okay, the work energy theorem questions, it's only one type of energy that's changing. So you'll have one for potential, one for kinetic. Okay, we've done lots like those. I would recommend, if you don't understand how to do those, that you watch some podcasts over the weekend, because I can't remember how many of those, okay, over the last few days. All right. So this is definitely written response, okay, at least for problem solving. Okay, and then obviously there's some fundamental stuff in the multiple choice about work energy theorem. Okay, conservation of energy, EI equals EF. Okay, so EPI plus EKI equals EPF plus EKF. It's possible that one or more of those values could be a zero, okay, in certain situations. Okay, in terms of context, conservation of energy questions are usually about what kinds of things. What was the most common example I used in class? Roller coasters. Yeah. Okay. Basically anything going down a hill, all right, okay, is kind of a law of conservation of energy situation. Okay. Whereas situations where there's obviously forces and distances like, bows and arrows, okay, and slingshots and things like that are obviously work energy theorem type contexts. Okay. That's what we talked about yesterday. It's only in the multiple choice. Okay, there could be some problem solving and some terminology related to efficiency. Okay. Okay, so remember, efficiency is the percentage of the input work that is actually doing useful work. Okay. There's not very much stuff in this unit when it comes right down to it, because I want you to be really good at the stuff that was in this unit, as opposed to be sort of good at so much stuff. Okay? So there's only those 7 things. Now, the test here. Let's tell you how many multiple choice, all that kind of stuff around there. All right, so there's 20 multiple choice questions. Okay, the front page of the exam, when you look at the back side of it, okay, is going to have your formula sheet. Right, so you won't be able to use yours. Right, the formula sheet will be given to you because I don't know how much little hints and tips and stuff you've written on yours. Okay, so you'll get the formula sheet there, and then underneath the formula sheet will be where you'll fill in your multiple choice answers. Okay. So starts out, okay, we got multiple choice questions on, like we said, thermodynamics, okay, laws of thermodynamics, systems, types of energy, okay, kind of a few people. Then there's some stuff about scalar and vector quantities, okay, knowing the difference, okay, knowing the difference between speed and velocity, distance and displacement, that kind of stuff. Then there's a graphing question, and then there's some stuff about acceleration. And then there's more stuff on energy, work and energy, conservation of energy, and efficiency. Pretty much exactly what I told you already. Okay, written response items. Graphing, acceleration, graphing, work energy, conservation of energy, and then one question that could be solved a couple of ways. So there's 7 written, 20 multiple choice. So if there's 2 graphing questions, do you have one on each type of graph? Yeah. All right, that gives you a pretty good idea what you need to do over the weekend.